In this video, we're going to be looking at how to solve for the internal forces of members by looking at this truss. We will use several properties of trusses, including 2-force members and 0-force members, to simplify the process. Then we'll use the method of joints and method of sections to determine the internal forces in several members. For the truss pictured here, we're asked to find the internal forces acting in the 4 highlighted members BC, DF, EF, and JL. In order to do this, we have to understand several important aspects about how internal forces work, what a 2-force member is, and how to examine a truss. First, to look at internal forces, let's take a generic member that was part of a rigid body and saw it in half. For most members, when we look at the internal forces, there are 3 forces present: an internal normal force, N, going parallel to the member, a shear force, V, which is depicted as acting in the direction causing clockwise rotation for each half, and an internal moment which would cause the member to bend into a smile. For our problem, and for the case of every truss, we are looking at a special kind of member called a 2-force member. A 2-force member is special because it has, as it sounds, only 2 forces acting upon it. Each force acts at one end, and there are no external loads anywhere else on the member. These forces will always be parallel to the axis along the member, and they will be equal in magnitude and opposite in direction. The convenient part about a truss is that every member is a 2-force member, so while analyzing the structure, each member will only have one internal force. Lastly, the final thing we want to look for before we get into our truss is called a 2-force member. As you could likely guess, this is a member that experiences no internal forces. For 0-force members, there are 2 main rules that we can check for to identify them. Here is a simple truss which has several 2-force members. For the first rule, we will look only at the forces in members at point A. If we sum the forces in X, the only force present is AB. So since it is in static equilibrium, AB must be 0. The same will be true for AC when we look at the forces in Y. This will establish the first general rule we can use to determine 0-force members. If at any joint there are only 2 members with no external forces or loads, and the members are not collinear, both are 0-force members. Next, let's look at all of the forces in members at point D. With the sum of forces in X, we'll see that DC and DE must be equal and opposite, and with the sum of forces in Y, it is clear that DB must be 0. This brings us to our second general rule for identifying 0-force members, that if there are 3 members at a joint and 2 of them are collinear, then the third must be a 0-force member. With all that in mind, we're ready to start looking at our actual truss. The first step will be to examine just the outside structure and the external forces to determine the reactions at the supports. The roller at K will be represented as simply a vertical force, KY. The pin at C will be represented as a vertical force, CY, and a horizontal force, CX. However, as we look at the whole body, we see that there are no other forces in the X direction, so CX must simply be 0. To solve for the Y components of these forces, let's start by taking the sum about the moments about joint C in order to find KY. Once we find the value for KY is 425 pounds acting up, we can look for the sum of the forces in Y in order to find that CY is 375 pounds acting up. With the values for CY and KY, we have all of the external support reactions, and we can examine the members inside our truss. We want to start by simplifying the members in our truss by identifying any 0-force members. Let's start by looking at joint A. Here we have 2 members, AB and AC, which are non-collinear, and there are no external loads of support. Using the first rule, we know that both of these will be 0-force members. Next, if we look at joint B, we notice that AB and BD are collinear, but BC is not. So from the second rule, we know that BC will be a 0-force member. We can say that JK is a 0-force member for the same reason. Now remember, BC is one of the members we were asked to find, so we've now finished 25% of our problem. Next, let's move on to finding the internal force in member JL by using the method of joints. To do this, we will imagine using some giant scissors to cut through every member at just one joint to look at all the internal forces as well as any external loads or supports at a certain joint. Separating joint L, we have to cut through JL and KL. For method of joints, you will only be able to have two equilibrium equations, so you can only solve for two unknowns at any given joint. A joint can have more than two forces acting on it, but it will not be determinate if more than two are unknown. When we cut open these members, we label each to have an internal force which is assumed to be positive when it's in tension, meaning it's pulling out on the member. At joint L, in addition to these two internal forces for JL and KL, there is a 100-pound load pointing down. Since all we're looking for from this joint is the internal force in JL, we can simply use this sum of forces in Y to determine it. The Y component for JL will have to be equal to the 100-pound weight acting down in order to maintain static equilibrium. Here we see that JL is 260 pounds, and our assumption that the member is in tension was correct, so the direction is upwards. Now we have found the internal forces for two of the members that we're looking for, and finally we will find the internal force in DF and EF. To do this, we will use what is called the method of sections. In order to find the internal forces for DF and EF, we will imagine taking our big scissors and cutting through each member until our truss is in two separate pieces. For the method of sections, you should never try to cut right through a joint. You should always make sure to cut through a member only once, and make sure to cut all the way through until you separate the section completely. For this section, we will cut through DF, EF, and EG to look at this portion of the truss on the left side. Again, we assume that each internal force is in tension, acting outward from each member. We'll start by taking the sum of moments about E and solve for DF. Only the x component of DF will cause a moment about E, and the distance for it is 5 feet. We generally say that counterclockwise rotation is positive, so here, based on the direction of our forces, both are considered negative. Since we got a negative value for DF, this means that our assumption that the member was in tension was incorrect. Instead, we say that DF has an internal compression of 487.5 pounds, which points downwards towards D. Now, to find the last internal force we're looking for, we will look at the sum of the forces in Y for this section. For EF, we found that the member has an internal tension of 16 pounds, and our assumption about the direction of the force was correct. With that, we have found all of the desired internal forces for this problem. In this problem, we learned how to work with the special properties of a truss, knowing that it is made up entirely of two-force members, as well as how to identify any zero-force members. For solving the internal forces of several members, we used the method of joints and the method of sections to understand how each member of the truss is experiencing a tension or compression due to the external load on the structure.